Okay, everybody, we're going to go ahead and get started. Welcome to another AC lecture. Let me just review a couple things that we talked about in the last class, in the last couple classes. I know in the last class we learned some new stuff. We went through a lot of material, but these two concepts are key to what we're going to do for the rest of the semester. So when we started the class, we talked about and we developed this form of representing an AC waveform, voltage or current, using what we call time domain. And I'm sure you know by now, but we'll just review it just in case, that we have here the instantaneous value, instantaneous value, and basically this t is the independent variable. So you tell me what time t to look at it, you put a number in for t, and I can tell you what the voltage is at that particular time. And of course, whatever I say here for voltage is also true for current. So just like there's an instantaneous voltage, there's an instantaneous current. This is the peak value on the amplitude. A voltage or current. Omega is a constant. Omega is the angular velocity. Angular velocity of what? This is the angular velocity of the actual generator coil rotating in the magnetic field in whatever rotating machine is producing this waveform. But we like to think of it as the angular velocity of the phasor that represents that rotation. We talked about phasors. And then we introduced this new term here in this. This is called the phase angle. The phase angle, or the phase for short. And what we said about the phase angle was that if I have a waveform, and when I draw my waveforms, I'll draw one where it kind of looks like just a normal sine wave starting here at 0. I call that standard position. But I said if I was able to grab this and move it back this way, if I can grab that waveform and pull it back, one point here, like this point right here, I know that's 90 degrees. So if I can grab this waveform and pull it back so that point is on this axis, then the waveform looks like this. If I can do that, that represents a 90-degree shift. I can pull it back that way. So now this angle right here will have a phase of 90 degrees, a 90-degree shift. And notice there's a plus or minus there. What we said in the last video was that if I pull it back this way, then that phase is a plus phase angle. If I start here, the green, and push it the other way 90 degrees or however many degrees, then I will use a negative phase. And so if you understand this idea, this time domain expression, you really get a lot of information out of here. For example, we know omega equals 2 pi f. So by just looking at that, knowing that, I can get the frequency. Of course, once you got the frequency, we know that the period is 1 over the frequency. So when I have a waveform written this way, when I have a waveform written in time domain, we can get a lot of information out of it. The problem is the analysis. When I want to do an analysis with this big, funky expression, it's not easy to manipulate this. If I want to do, let's say, some of the stuff I did in DC, like even the Ohm's law calculation, it's kind of cumbersome with this equation. But imagine doing something like mesh analysis, or imagine doing something like superposition with this equation. That would be terrible. And so we looked at another way of representing this. This quantity, this voltage quantity, I introduced this idea of phasor domain. So what's a phasor? Well, the first thing we talked about was that there's only two kinds of phasors. You can have a voltage phasor or a current phasor. So we're going to talk about other quantities this semester. We'll talk about other quantities, and we'll learn some of those today. But remember, the only two that are allowed to be phasors are voltage and current. So a phasor is basically a representation of this where the magnitude is in RMS, and then I express the phase over here. So to get this value, the RMS value, of course, I just take the peak value and multiply that by 0.707, and that changes the peak value to RMS. So now I have the RMS value. And then get the phase angle, you don't have to do any calculation. All you got to do is look right here. And whatever that is, if it's negative, you write the negative phase angle. If it's a positive, you write that as a positive phase angle. And if there's no angle there at all, then this angle here would be 0 degrees. Now this is interesting because we talked about in a previous lecture that this parenthesis, what you put in there is called the argument. And you know that when you do a calculation with this, that you need to have this in radians because the argument takes radians. But when you express it, usually what they do is they'll have this omega t, right? But they'll express this part of it in degrees, and that's just for convenience. So it's kind of mixed up in there. You don't really do a calculation with the degrees. You would not have that in there with the degrees. But this just shifts the sine wave to the left or to the right. So this turns out to be really important for the reason I said before, whereas that what we like to do in this class is pretty much everything we did in the previous class in DC, but the equations are complicated. Number one, we got several ways to represent AC voltage and current, and even if we represent it as just this function here, it's just a lot. It's like, again, remember, what if you had to put that into determine it to do mesh analysis or nodal? You wouldn't like that at all. So it turns out that if we express quantities in phasor domain means that we have a magnitude of RMS, and then whatever the phase angle we get here from our time domain. Now, what do we mean this phasor domain, time domain? Well, this idea of domain comes from the allowed value of an equation or function. Usually you have x and y. You have a y equals something with an x on the other side, and the x would be your domain, and the y would be your range. So here we don't use the x, we use the t. So our independent variable would be t. The values that we're allowed to put in for that variable is what we mean by domain. So they name this time domain. Now here we don't have anything unknown. We don't have anything that we can substitute values in. Like, we don't show this as a function. We just show this as an actual number, a magnitude and an angle, a phase angle. But look at how we express this. We express this value in RMS. Now, I spent about probably 30 minutes in the video before trying to explain to you what exactly is RMS. And the reason I want to explain it to you is because I want you to know why we can do the things we're going to do this semester. What RMS is an equivalency between AC and DC in terms of heating effects. Now, I won't go through details of it again, but you can review the video. You remember when I had the experiment on the board with the water and the thermometer, and you remember how that went. So basically what RMS says is if you have an RMS value for AC and a DC value, let's say you have a 100-volt RMS value AC signal and a 100-volt DC signal, we're saying that the heating effects or the amount of electrical work that they do is the same. And I don't know who came up with that idea, but it's brilliant. Because, see, when we deal with work or energy, there is no AC work or energy or DC work. It's just energy. There's no AC energy and DC energy. It's just energy. So energy is energy is energy. So by equating the two, what we do is we remove from the whole equation whether we have something like DC that's constant or AC that's varying like a waveform. And we just look at how much electrical work can it do. So basically, by expressing this in RMS, it allows us to take this signal and treat it as if it were DC. Anything we did in DC, we can now do it in AC as long as we express it in phasor form. And so we spent some time right at the end of the last class just practicing going from time domain to phasor domain. And if you didn't see the video, you want to watch it, but it's pretty simple. You just take whatever the value is here, multiply by 0.707 to get your RMS value, and then whatever the number is here, that's your phase, you put it over here. Just be careful to make sure if there's a plus or minus sign there, you show the same over here. And now we have a phasor that we can basically do whatever we want to do. Whatever you can do in DC, you can now do it with this, because a phasor basically is an equivalence equivalent DC. Now, the way I express a phasor, I don't know if I mentioned this last time, a phasor, the way I'm going to show it's a phasor, the way I have that V there, that's just a voltage, but if I put this bar over the top like that, I call it a hat. So V hat is a phasor. So this is V phasor. And if I say V phasor, or I can have I with a hat on it, that's I phasor. And that means that I got to express that as the RMS magnitude and some angle. But it also means that I can treat it as if it were DC. So it's important that you understand how to go from time domain to phasor domain. And once you're in phasor domain, that you understand now basically this is an equivalent DC. We could treat it just like we would treat DC. And so at the end of the last lecture, we were practicing on the sheet going from time domain to phasor domain. There's 4 problems listed there, and we did 3 of the 4, but we didn't do number 4. So if you have that sheet, go ahead and take it out. It's the one it's titled phasors, and there are 4 problems at the bottom of it. So I'll give you a second to get it out. And if you don't have it, don't worry about it. I'll read it, but it is up on Blackboard if you want a copy of it. And this will give you a demonstration of how powerful phasors are. All right. So the problem says you have 2 devices. They call one A and one B. 2 devices A and B are connected in series in an AC circuit. The frequency across both devices is 60 hertz. It says that VA, voltage A, is 50 sine 377t plus 30 degrees, and VB is 30 sine 377t plus 60 degrees. They want you to apply Kirchhoff's voltage law to find the total voltage across the whole circuit. And they want you to sketch the circuit before you do the analysis. So I read it, but I think, let me make the picture, it'll be a little easier to understand. So what they're saying is that we have 2 waveforms, 2 generators, or whatever. We have two AC generators. So here's one, and here's the other one. We're going to call one of these A and one of these B. And they're hooked up in series. So I've got 2 generators hooked up in series. And then they give you this voltage right here. They say that voltage is given by the function VA equals 50 sine 377 T plus 30 degrees. And they give you this voltage. VB is 30 sine 377 T plus 60 degrees. And what they want you to do is apply KVL. Now that's a DC thing. KVL is DC. Kirchhoff's voltage law says that if I have 2 sources together, I should be able to add them and come up with the total voltage. So that's a DC thing. So how would I do that? How am I gonna get the value for KVL if I have these sine waves and everything is varying? How am I gonna do that? Well, before we looked at phasors, there wasn't a way to do it. But what we're going to do is we're going to change this and express VA. We'll change it from time domain to phasor domain. And then we'll take VB and we'll express it in phasor domain. And then I'll show you how you can actually take it in phasor domain. And then we can actually come up with the answer we're looking for. So I'm going to need your help. What you're going to do is get a calculator. Make sure you have, for today's lecture, you need to have pen, paper, and calculator out. Take that out, and there'll be several things that we talk about that you want to remember. So I would also have a notepad where you can write, just jot some stuff down. So I want to add these two up, and there's no way to do it like this, no easy way. So what we're going to do is we're going to convert these to phasors. So take out your calculator, and can somebody convert this to phasor form? Let me know. And the way I would express that, remember, this is VA, so I would show it like this. VA with a hat on it. Then I need a magnitude and an angle. So what would this look like as a phasor? Anybody? What do I do to go from time domain to phasor domain? What are the steps? Okay, so to express this as a phasor, remember this is the peak value. A phasor, I need the magnitude, which is in RMS, and then I need a phase angle, and I just look right here to see the phase angle. So if somebody take 50, this is 50 volts peak, what would that be in RMS? Tell me what that is in RMS. And I need your participation, because this is going to be a long lecture if you don't help calculate.
$35.35.
All right, how'd you get that value?
50 times 0.707.
So all right, he took 0.707, multiplied this. That's how you go from peak to RMS. So what I'm going to do right here, I'm going to write that as VA, but I'm going to put a hat on it to show you it's a phasor. And then we got 35.35 at an angle of, and I just look at the phase angle that was stuck to the time domain, it was 30 degrees. So this is at an angle of 30 degrees. Now what I like to do is when I show my units, because I got a V there, and to me if I put a V there like the book does, that looks funny to me. Sometimes some books, when they show a phasor, they'll do this. They'll say 35.35 volts, then they'll put the angle like that. And I don't like that way either. If you want to do it the book's way or you want to do it this way, you're fine. But I like to do it this way, but then I put a bracket around here so I know that's a unit. So that's the way I do it. If you want to know what that means, it just makes it kind of stand out as a unit. So everybody should be able to go from time domain to phasor domain. So let's express this now as a phasor. What would this one be?
The RMS is 21.2.
Okay, so it's 21 point what?
21.
21.21. And the angle is 60 degrees. My units are volts. Okay, so now what I can do is treat this as if it were DC. Now, what do I mean by treat it as if it were DC? What I mean is anything you did last semester, if you had to meet for DC, any of those Thevenin's theorem, superposition, anything we did last semester in DC, we can now do it with AC because this acts just like this is a DC equivalent. It's a DC equivalent. It acts like DC. This is the power, not AC DC concern, but just power, energy, work. And there is no AC DC work. There's just work. And so once we render it like this, we render AC and DC to be the same or to be equal, and we can do whatever analysis that we would normally do with DC. But I got to show you something else before we actually do it. Now, the other thing we talked about the other day, very important, we use complex numbers. And you might notice something about this phasor. Remember there was two forms of complex numbers. One way to write a complex number is like this. I can have like A plus JB. So you tell me how far over and up to go, that's rectangular form. But the other way to write a complex number is you give me a radius vector and an angle, and I can still get to that same complex number in the complex plane. So I can write it this way, that's rectangular form of a complex number. I can write it this way, that's the polar form of a complex number. So as we were going through this, it might look like, or you might say, hey, this looks an awful lot like polar form of a complex number. It looks just like it. As a matter of fact, let me show you exactly how this works. Do you guys know what a Venn diagram is? A Venn diagram. They use these in philosophy and math a lot, a Venn diagram. And it's pretty easy to understand. Let me show you a Venn diagram for this. So what you do is you draw these circles. So I got this circle. And this circle right here represents all complex numbers. Okay, so I got the Venn diagram. And then here I'm going to put another circle. And this represents phasors. So this is the Venn diagram for complex numbers and then phasors. And the way to understand the Venn diagram, it helps you to see that if you think about what it's saying that a phasor is a complex number. That's why I have it in the circle of complex numbers. A phasor is a complex number, but not all complex numbers are phasors. If I have something right here, if I have a number right here, then whatever that number is a phasor and a complex number. But it's possible to have a value over here, and I have a complex number that's not a phasor. And you'll see examples of both of those tonight. So you'll see phasors. A phasor is a type of complex number, a special complex number. It's a voltage or current. But you also see complex numbers that are not phasors. So the Venn diagram helps us to understand it, at least to see it clearly. All phasors are complex numbers, but not all complex numbers are phasors. And so if you understand that, what this means is, even though these are phasors, they're complex numbers. Therefore, I can convert these to rectangular form, and I still have a phasor. It's just expressed in rectangular form because it's really also a complex number. Now you can kind of see where I'm going with this. If you remember, when we dealt with complex numbers, at the very end of that lecture, we did some calculations with complex numbers. We did addition. We did subtraction. We did multiplication. We did division. We did examples of all of those. And what we said was that you can see from those examples that when you're adding or subtracting complex numbers, it's easier or best to do that in rectangular form. When you're multiplying or dividing complex numbers, you want to be in polar form. I don't know if I said that right. Add, subtract in rectangular form, multiply and divide in polar form. And so since we can treat since phasors are complex numbers, we can go ahead and convert these to rectangular form, and then we can add them up, because that's what Kirchhoff's voltage law says. Kirchhoff says I should be able to add this voltage to this voltage and get the total voltage. And I can do that if I convert these over to rectangular form, add them, and then convert them back to the polar form. Normally, when you express AC or voltage or current, normally you express them in phasors. You express them in polar form. Not always, but most of the time you do. There are a few circumstances where we want to have these in rectangular form, and you'll see those this semester. But for the most part, you always express voltages and currents as phasors in polar form. Now, I failed to mention one thing. In the actual reading of the problem, when we had these two forms in time domain, they mentioned the frequency was 60 hertz. And that's important because in order to do any of the math that we're doing, any of the phasor stuff we're doing, the frequency of the time domains or the frequency of the phasors have to be the same. That's mentioned in that handout. Now, you kind of can tell that the frequencies were the same. I don't know if you have the sheet right in front of you, but if you go back and look at the omegas, if the omega for the waveforms are the same, that means the frequencies have to be the same. So if the angular velocity for any waveform is the same as that of another, then the frequencies have to be the same. But they pointed it out because earlier in the paper, they did mention the fact that in order to do any of this complex algebra, which is what we're doing, the frequencies have to be the same. If I have two waveforms with frequencies, we can't do any of what we're doing right now. The thing we do in this class, we're going to assume that the frequencies of all the waveforms are the same, and we can move forward with our analysis. So if I want to do this, what I got to do is convert this over to rectangular form. Both of these voltages have to express in the rectangular form. So I don't know if you remember how to do it. It's been a little while, but I think after that homework sheet you did, or not the homework, but the lab, you guys should be expert at this stuff by now. So, but just in case you forgot, I want to convert this to rectangular form. So in rectangular form, I have a real part. The real part would be the radius vector times the cosine of the angle. And then the imaginary part, the part with the J, is my radius vector times the sine of the angle. So here, just think of your magnitude here as your R. So think of this as your radius vector. That's your R, and that's your R. And so let's convert this over. Now the way you would write this down, the way I like to do it, to show I'm doing this conversion, this is in polar, so I'm going from polar to rectangular, and I put these two columns here. And then when I do my math, I don't actually have to show the math. I can just show this right here, and that represents all the math that you would do to convert this over. So let's convert it over. Let's do the first one together, and then you guys can just tell me what the next one is. So I want to convert this first one to rectangular form. So to get the real part, I got to take 35.35 cosine of the angle, it's 30 degrees. And that'll give me the real part. And then to get the imaginary part, I got to take 35.35. It looks like an S. My 5 looks like an S. 35.35 sine 30 degrees. So you go ahead and do those calculations for me and let me know what you get for the first one. Let me know what the A part is. But make sure your calculator is in degrees and not radians. The only time you should have it in radians is when you're doing the actual calculation, trying to figure out the instantaneous voltage or current using that time domain formula. Other than that, you're in degrees. So change it to degrees and give me cosine 30 times 35.35 and tell me what that is.
$30.61.
30.61 plus J, and now this one. What is it?
17.67. 17.67.
Okay, I'm looking around at 17.7. Now I don't have enough room to write my units, but you just write volts with a bracket on it. So on your paper, write the volts over here so you get your units right. So now everybody sees how to convert this. So now everybody, I see 1, 2, 3, 4 plus 2. So the 6 of you, well, I guess the people on the phone can't participate. You can just listen. But if you have, if you're online through the link, go ahead and convert this one over. Tell me what to write when you convert this.
I got 10.6 plus J 18.3 or 18.4.
All right. And again, put your volts there. Now, since we have it in rectangular form, we can add it. So let's add these up. I got a 1.
Should there be
I
a
got a
J in front of
2.
that 18 or it doesn't have to be?
Yeah, thank you. Right. It should be a J there. Okay, so I got a 1, a 2.1, 4. I think that's right. Check my arithmetic because I'm not good at doing my arithmetic in my head. And then here I got, what is that? That would be 15, so that would be 35. Is it 36.1? Is that right? Is this right? 36.1?
Yeah.
Okay. Now, you don't leave it like this. However you were given the waveform is what you want to show. So now I got to take this number and let me write it over here so it's neater. I got 41.21 plus, and again, there should be a J here, J 36.1 volts. So I've added these up, and now what I got to do is go back to polar form. You always want to show your current or your voltage as phasors in polar form. So I'm going to go back. Now remember, to go back, what you got to do is to get the radius vector left, you got to take A and square it, B and square it, take the square root of it, and to get your phase angle, you got to take the inverse tangent of B over A. Okay, and so in this problem here, this is A. This part right here is A. And then this is B. So put these values into here and give me the magnitude of the radius vector that represents the sum of these two instantaneous voltages. What would that be? Give me R. Mike, give me this value here.
Got a 54.8.
All right, now to get my phase, we have to get the phase angle, you have to take the inverse tangent of B over A. And so that would be the inverse tangent of B is 36.1, A is 41.21, and give me that angle. I gotta change this marker out. I got a lot of miles on my markers. I've been through a ton of them. Okay, so if you do this, inverse tangent of 36.1 divided by 41.21, what would that be?
Got 41.2.
All right, so I got 41.2 degrees, and then I would show volts here. So that would be the sum KVL of those two waveforms. Now notice all the going back and forth we did between forms. That's why it's really important that you're able to do that. So what I have here is the new total voltage for this. If I add these up, I'll just call it VT and put a hat on it because that's a phasor. Now they didn't ask us to do this, but how would I convert this back to time domain? How would I convert that back to time domain? What would I do? Anybody? Let's do that. Let's just do it for fun. Convert it back to time domain. So to have it in time domain, I need to express it like this. V equals VP sine omega t plus or minus the phase angle. So the first thing I know is, well, this I know, right? That I know that the frequencies are the same, then the omegas are the same. If you go back at the problem, that right there they gave us was 377 radians per second. So that I know. And what else do I need to do? What else do I need to do to get it in this form? This right here is what? That's the phase angle, right? So that goes here. And then all I got to do is get this value. But that comes from here. This is RMS. So I got to change it back to peak. So let's see if we can write this back in time domain. So if I want to go back to time domain, I'm going to say my script V is equal to, well, to get it to RMS, you multiply by 0.707. So to get it to peak, you take this and divide by 0.707. So what's 54.8 divided by 0.707? What would that be? $54.8 divided by 73.5 sine omega they gave us was 377 T, and then the phase would be right here, plus 41.2 degrees, and that would be my total voltage. So what happens is, in series, these two, even though if you put we haven't really talked about the AC equipment, but the device you're going to use to actually see the waveform is called an oscilloscope. And I think, I think your lab this week is multimeters. I think next week you'll do some looking into some oscilloscope. But if you put an oscilloscope across here, you see the waveform that represented VA. You'll see a single waveform. If you put it across here, you'll see the waveform that represents the instantaneous voltage for VB. But if you put it across the whole thing, you see this. These two actually combine into one single big sine wave that looks like this. That has this peak value, the frequencies are the same, but now there's a phase angle. So that's a good exercise. And what this shows you, it shows you how we can use time domain to go to phasor domain. And once we're in phasor domain, we got two things going on in phasor domain. Number one, since a phasor is an RMS, we can treat it as if it were DC. And number two, since a phasor is a complex number, we can take it to polar form or back to rectangular form, which means we can do multiplication, division, subtraction, and so forth. We can do all that. And that makes this stuff kind of nice. But you can see it's a lot. You got to be able to quickly go between the forms, which means you don't need to look at any equations or fumble with any. You got to know it cold. You got to know how to go between one and the other. And that was the purpose of doing the lab and the lab one and all the other practice stuff that we did to get good at doing stuff like this. But we just applied KVL to two circuits that had generators and produced sine waves, and now you see how it's done. So any questions over, let's say we talked about complex numbers, we talked about phasors, we talked about going from time domain to phasor domain, and here we even went back from phasor domain to time domain. If you have any questions over any of the topics we discussed so far, either today or from the last lecture? Any questions? Okay, well, if there are no questions, I want to move on to the next topic sheet. I don't know if you had time to print it out. I hope you did. It was the one from last week, so I didn't put anything new up. I put a lot of stuff up last week, and hopefully you have it printed out. But if you don't, I'll read it. It's just better to have it printed out. So this is the topic sheet that deals with AC oppositions. So it says at the top, response of basic R, L, and C elements. So let me put that on the board. So it says response of basic R, L, C elements. And what does that mean, the response of basic R, L, C elements? Well, you know what the R, the L, and the C mean from before, from DC. R is a resistor. L, we didn't do a whole lot with inductors, but you know L is an inductor. And C is, of course, a capacitor. So the word response, what they're asking is, how do these components, how do resistors, inductors, and capacitors, how do they behave in an AC circuit? How do they behave? That's what that means, response of basic RLC elements. Now, if you had me for DC, we spent like almost the whole semester talking about resistors. We know resistors divide voltage, resistors can limit current. We spent a lot of time talking about capacitors. We know you can charge a capacitor, you can discharge a capacitor. You know a capacitor takes 5 time constants to fully charge, 5 time constants to fully discharge. And we talked about the inductor. We know that we spent just a little time talking about inductors, which is an inductor is just basically a wireless coil, and that the inductor, when you charge an inductor, what you do is you build up a magnetic field around the inductor. So the energy is actually stored in the magnetic field. And when you release that energy, the magnetic field collapses. And when it collapses, you basically have Faraday's law happening. You have a conductor. The inductor itself is a conductor. You have a magnetic field. And since the current that sustains the magnetic field is now going to zero, the magnetic field is going to collapse, giving you movement. And so the inductor itself actually acts like a counter EMF or a voltage source that can send energy back to a system or radiate it off as a radio wave in the free space. So we talked about these, but I just described DC behavior for these elements. What this wants to know is how they behave in an AC circuit. And so how do they treat voltage and current when I apply voltage and current to these components, and the voltage and current is an AC voltage or AC current. That's what we want to look at. And so to understand that though, we have to go take off our electronics hat and put on our math hats. We got to talk about a math concept. Now, I'm no mathematician, so I'm not going to use all the correct languages or words and terms, but I do know the concepts. And I did teach high school math for 4 years at a charter school. I taught advanced math, but I'm more of a physics. I guess I'm a crossbreed, physics and the engineering kind of together. So the concept we're going to talk about is a concept called the derivative. Now, if you had calculus, you know all about the derivative. The calculus is about taking a derivative of something or integrating something. And I'm not going to go into the theory of that, but let me just give you the basic concept. And you don't have to do calculus. That's not what the point of this is. The point is I want you to understand where things come from. Now, this is big to me because I'm spending valuable time that I could be using to go right into the math so you can solve the circuits. Most professors would just skip over this if they even know about it. But I want you to know where things come from, because I think if you understand the first principles, the basic principles, then when we get the more difficult material, you can understand why it is the way it is, because you can relate it back to the first principles. I just think that's a better way to teach. So I choose in my classes to take time and examine the first principles, even though it's going to take some time away from time that we could be calculating. But hopefully you will appreciate it. So let me start by just this idea of change. How do you represent change mathematically? And you might not think about it this way, but one way you're taught to do this is, let's say you have a coordinate system. Now they usually use X and Y, but I'm going to use T and X for my independent variable and my dependent variable. And the reason I'm using T here, in physics and engineering, you have these rates of change, and a time rate of change is very important in physics and engineering. So by putting T here, we get time rates of change, and you'll see what I'm saying in just a second. But one way we can represent change is just the idea of slope. As a matter of fact, that's what slope means. Slope means change. We're talking about the slope of a line. It gives us information on how fast or how slow something is changing, or if something is changing or not. So for example, you know that if I have a line that's sloped up this way, as I go from left to right, if I go up, you know that represents a positive slope or a positive change. You can say it's increasing. Whatever it is increasing. If I have money in the bank, and this is the time I have that money in the bank, if I show this, that means my money is increasing. If this is in months, and this is in dollars, if I take the slope of this, I get dollars per month. That's a change. You know, or you've been taught that if I have a slope that goes the other way, and that represents a negative change. So this is decreasing. If this is the money in the bank that I have, I don't want that. That's a bad thing. That means my money is decreasing. And the more steep, the faster it's decreasing, or faster it's increasing. So you recognize this as a negative change and a positive change, or maybe this one right here. I have a horizontal line, the slope right there, they use an M for slope. That would be zero slope. Zero slope doesn't mean I don't have any money in the bank. If I have, that might be $1,000 there. And all that zero slope means is that the money isn't changing. It's constant. So a zero slope is not zero value. It just means zero change. And then the other thing I can have is I can have a slope like this, where I have a line like that, and we say that that slope is undefined, and we show that by showing infinity. So slope tells us how fast or how slow something changes. And so if I show an example here, let's say I have a line. I guess I can do it in black. So any old line, I'm just going to take a line like this. And let's go through the process of finding the slope of that line. So if I want to find the slope of the line, what do I got to do? How do I find the slope of a line? And the reason I want to do this, even though you've done this in math, is because we're going to take this and apply it to something that's not a line. And this is going to help us understand how to find the slope of something that's not a line. If it's not a line, it's a curve. So how do we find the slope of a curve? So if I want to find the slope of this line, here are the steps. The first thing you're going to do is you got to get 2 points. So I'm just going to pick any 2 points. So I'm going to pick a point here, and I'll pick a point right here. Once you pick the 2 points, you name them. So I'm going to call this point 2 and this point 1. So here's P2 and here's P1. Once we do that, then it's a piece of cake, because now we got coordinates we can talk about. Like I know the coordinates of this right here would have coordinates of x2, and over here, actually using t's. So this would be T2, T2, and over here, x2. And the same here. The coordinate here would be T1, and the coordinate here would be x1. So now I have points, and I know their coordinates. I can find the slope, because the slope, they taught you in math to find the slope, and I don't know what the M stands for. I think it's Latin for something. What you do is you take in this case, the x values. So what I want is this distance right here. I want the distance between these two. And to get that, I got to take this piece and subtract that piece. So I'm going to call that piece delta x. So what I said is I'm going to take x2 minus x1 and divide that by this piece. We'll call that delta t. And to get delta t, I got to take this piece and subtract that piece. That'll leave me with that piece. Well, that's easy to do. It's just going to be t2 minus t1. And if I gave you values for x2, x1, t2, t1, you can put it in here and you can give me the slope. Now, notice that we refer to this difference right here as delta x. Another way to think about this is delta x over delta t. And that's the operator in math. They call it change in. The change in x over the change in t gives me the slope. And so I can write it this way if I want a full-blown equation. And this is a shorthand way. We recognize that to be the change in x over change in t. So this is pretty simple. Once you give me the numbers here, I can put them in there. I'm good to go. No problem. So finding the slope of a line is kind of trivial. Once you see it, do it one time, piece of cake. Well, what if I had something that's not a line? Because we're dealing with stuff in AC that ain't a line. So what if I have something that's not a line, but I want to find the slope of it? How would I find the slope of something that's not a line? Well, if it's not a line, it's a curve. So let's look at that scenario. How do I find the slope of a curve? So I'm going to make up any old curve. Here's my axis. T and X again. And let me make a curve. So I'm going to start my curve. I guess I'll make it like this. There's my curve. Well, we got a problem already that I see on this curve. This curve has the. Let me see if I can find. I need like a. Hold on. Here we go. So here's my. If I'm right here, that slope looks like it's positive. If I'm right over here on the edge of this, it's negative. If I'm right here on the flat part of that, it's 0. So right off the bat, I got a problem that I don't know how to solve yet, because the problem is I got different slopes. So when you say what's the slope of that curve, I'm going to say, well, where do you want me to look? So the first step in defining the slope of a curve is telling the person where to look. And the smart people way of saying that, the math way of saying where to look, is define an interval. Define the interval. Okay, what I want you to do, I want you to find the slope between this point and this point right there. Tell me what the slope is between those 2 points. Okay, all right. Well, let's name these points. Let's call this one P2, and we'll call this other one P1. So by showing where to look, we've defined the interval. And what do you mean by interval? Well, an interval is just a piece of an axis. So an interval is just a piece of the x-axis or a piece of the t-axis. So by putting a point here and here, I've defined an interval. This right here, if that's P1, then that's X1. And if this is P2, that's X2. And guess what? My interval is this. From there to there, that's my delta X. I'm using X's, I should be using T's. That's the only problem with using a T here. I'm so used to writing X that I automatically go revert to that. So this is not right. This should be T2 and T1. Sometimes I think Jacob catches me on this, but he's just too polite to say it. I know he had to see it. T2, T1. And so this will be my T interval. I'll just show it like that. And there's also one over here, right? I can do this one, and I can do that one and get a delta X. So when I say define an interval, I say look between this point and this point. And by definition, when you put those 2 points up there, you've defined a T interval and you've also defined the X interval. Okay, well, okay, that sounds good, but I still don't know how to find the slope. How do I find the slope of that? Well, the answer is, I don't know yet. But here's what I do know. I know how to find the slope of a line. Not a curve, but a line. So what if I use that to help me to understand what this slope might be? In other words, what if I do this? What if I neatly, and I wish I had a straight edge, but I don't think I have a straight edge. Oh yeah, I do. I found one. I found a straight edge. Yeah, so this is a piece of stuff that you put on drywall and you attach a shower tile to it. I was looking for something to keep this board down here on the board, so I bought this from Lowe's and cut it off because the board was moving around when I was writing on it. So I screwed this to it to clamp it up against there, and it worked out. It works out pretty well. So I threw this on the ground like 3 months ago, and now it's a straight edge. So what I can do here is, what if I do this? What if I draw a line like this? And you might say, okay, well, why would you want to do that though? Why would you want to draw a line through those 2 points? Well, here's why. I don't know how to find the slope of a curve, but I do know how to find the slope of a line. And since, like, let's say I choose any value on the line, any random value. So I'm going to close my eyes and just say that point right here. So that point right there, I know that it is not the exact slope of the interval of the curve because there's distance between that point and the one right above it, this one. So that distance between these, like if I was over here, the distance would be shorter. But the fact that there's distance between the value here and the value there means that the slope that I'll get if I take the slope of a line is not really the slope of the curve, but it gives me a number that's close, if you can follow what I'm saying. So what I'm saying is, I don't know how to take the slope of a curve, but I know how to take the slope of this line. I just do this, right? I do exactly what we did in the beginning. This gives me the slope of that purple line. And what I get is a value that approximates the slope of the curve. Now I got to give you a name. I have a line that cuts a curve at 2 points. A line that cuts a curve at 2 points is called a secant. A secant. And the secant line, when you take the slope of the secant line, it gives you the average slope across that interval. And let me say that again. I have a curve, and I cut that curve with a line that cuts the curve at 2 places, place 1 and place 2. A line in math, a line that cuts a curve at 2 places is called a secant. And if I take the slope of the secant line, which I know how to do, I can take the slope of a line all day, it will approximate the slope of the curve about the interval that we're told to look. So even though this slope of that line is not the exact slope of the curve, it gives me a number to work with. Before I didn't even know how to do it, I didn't have anything to work with. Now I got a number that I know is close. But what if I want to get closer? What if that's not enough? I want to get closer. Well, what you could do is you can take these 2 points, P2 and P1, and I can push them closer together. Let's do that. Let's say I move P1 to here. That's my new P1. And I move P2 to here. So get rid of these. And now P2 is here. And P1 is there. Now let me draw my secant line. So now when I draw my new secant line, look what I do now. So now my new secant line, if I take a point on this secant line, now look how close it is to a point right above it on the curve. What that means is that when I take the slope of this line using this equation over here, which I know how to do, the slope of that second secant line is going to be much closer to the slope of the actual curve. But the point is, look what the trade-off was, my interval got smaller. So now my delta t interval is smaller than before. Well, okay, well, I can keep doing this, man. This is kind of cool. Let's keep pushing those points together. And what that's going to do is, it's going to give us a better and better and better number for the slope of the curve. The secant line is going to get closer and closer to the actual slope of the curve. But the trade-off is our interval is going to be smaller and smaller and smaller. But let's just see what happens. What if I just keep pushing these points together? Maybe I take P2 and P1 and put them right here. I got one here and one there. So now when I draw my secant, what does that look like? Well, it looks like this. Wow, they look really close now, like they're almost right on top of each other. But they're not. If you take a magnifying glass or a microscope and look really close, since the dots are still separated, there's actually a little bitty space, microscopic space, between my purple line and my black curve. But if I take the slope of that third secant line, I'm really close to the slope of that curve. Look at my interval now. My interval is this skinny. My interval is getting skinnier and skinnier. Here's what they do. without going into a lot of theory, they say I'm going to take this interval. Now remember, this is delta t. What happens if I let delta t approach 0? Not get to 0, but approach 0. In other words, what happens if I keep pushing these points together and they get closer and closer and closer together till the distance between them is almost 0. Now, I remember being a young, handsome physics student at Xavier University back in the 90s. And you had the math people over here and the physics people over here. And this is where the math people and the physics people agree. Or not agree, but disagree. Because the math people, as you keep putting these closer and closer and closer, the math people say they get so close that they become 1 point. Which is okay to think about it. But the physics people say, no, they just get, I like this word, infinitesimally close. Let me say that again. The first time I heard that in physics as a student, I just blew my mind. Because I heard of infinite, how big something is. But when the teacher said that these points were infinitesimally close, infinitely close, but yet not touching, that blew my mind. In other words, the distance between them is so close, they're almost touching, but not quite touching. And the math people argue, well, you know what? If I have 2 points that's so close, they look like 1 point. If you step back far enough from it, they look like 1 point. But the physics people are going to say, no, there's really something between them. There's a little tiny interval. It's just that interval, that in this case, delta t, is infinitesimally small. And I don't care which way we argue. Here's what we're going to do. We're going to treat these things. It doesn't matter if it's 1 point or if it's 2 points that's infinitesimally close. Either way, if it's 1 point, there's nothing to measure. And if they're infinitesimally close, we still can't measure between them to get the width of the interval. So either way, we're going to treat them as if they're 1 point. And if we treat them as if they're 1 point, we push these together, we treat them as if they're 1 point, it makes sense to talk about a delta t, a delta x, and a delta t, because we can't get the x1 and the x2 or the t1 and t2 because the points are so close together if I push them together close enough. So what they do is when we get down to where they're so close that we can treat them as if they're 1 point, instead of writing delta x, they write dx. And instead of writing delta t, they write it dt. So this right here, this change in x over change in t, which is what this is, our regular slope formula, this is the slope of a secant line. A secant line. A secant line is a line that cuts a curve in 2 places. And I can take the slope of that because I can get the x2, the x1, the t2, and the t1. But when they're so close that they look like 1 point, when these are so close, it looks like 1 point like that, then I can't get in there to measure in between them. So we're just going to treat the 2 points as if they're 1 point. And so I'm going to give you another line, that when I push these points so close together till they look like 1 point, then it looks like this. I got my 1 point right there. And then I got a line that goes through it. I don't know where that, oh, my green marker must have fell. Yep. It looks like this. So I have a line that touches a curve at 1 point. A line that cuts a curve at 2 points, we said that was called a secant line. If you take the slope of a secant line, it gives you the average slope for that interval between the 2 points. But if you push the points so close together that they look like one line or 1 point, and then you draw a line through that single point, then the line now is called a tangent line. A secant line cuts a curve at 2 points. A tangent line touches a curve at 1 point. The slope of the tangent line tells you the slope of the curve at that point. So if I take the slope of this line, how would I do that? Well, I'll just take a point here, call it P1 or P2. Take a point here, call it P1. And then I got right here, I got an X. Well, I guess I'm using T, so I'm getting that confused. But you got my point. I got once if this is X and this is T, once I do that, I get a T2 and I get an X2 and a T1 and the X1. I can put the numbers over here and I can get the slope for that line. But the slope of the line is going to be the slope of this curve at this point right here. The takeaway is the slope of a tangent line tells me the slope, it tells me the average slope of a curve between 2 points, and the distance between the 2 points is called the interval. If I make the interval small enough so the points look like they're touching each other, I take the slope of draw a line through it, then the line that touches the curve at that 1 point is called a tangent line, and the slope of the tangent line tells me the slope at that particular point. Now, when I have this slope of the tangent line, this is the secant line slope, but this is the tangent line slope, that's called a derivative. So if you follow the handout, they mention the term derivative. I'll write it down. So the slope of a tangent line is called the derivative, and the derivative tells us the slope of a line at a point on the curve. Now, I don't know because I can't see your faces. You're not saying anything. I don't even know if you guys are really there. You could put the camera computer on and walk away from it. I don't know what you're doing. So I don't know if you're following this or not, but hopefully I'm going to show you an example that if you're a little confused, if it's not crystal clear, hopefully this will drive it home. The point is that I can take, imagine this is my tangent line. That's my tangent line. And this is my curve. I want to find the slope. Well, all you got to do, you can put this tangent line anywhere you want and then get 2 points off of it and you can calculate the slope. But just remember, it's the slope at that point. So like if I put it right here, let me get a marker. If I put the tangent line right here, then that might be the slope at this point if this tangent line touches that curve at that point. But I can see right off, I don't know what the value is because I don't have the numbers, but I can see right off that that slope is positive. If I go right here, I can see right off that that slope is 0. If I go right to the edge, I can see that the slope of that tangent line is negative. And most of the time, well, at least for what we're doing, we don't care about the actual value. We just want to know, is it negative? Is it positive? Is it 0? Positive, 0, negative. And the more up like that is, the faster that slope is changing. The more down like that is, the faster it's changing in the 0 direction. If it's like this, that means I have infinite slope. So just by looking at a line in my mind, I can visualize this line touching the curve at different points. I can use this to find the slope of curves at different points. And that tangent line, the slope of that tangent line, in math, they call that the derivative. You know, when they say that, all they mean is the slope of a tangent line. Okay, well, assuming you understand part of this, how is it useful for us? Well, I'm going to show you how this is useful. So, up until now, we've been talking about what, motors and generators. We didn't talk about motors. We talked about generators and the right-hand rule and cross products and vector products and phasors. And a lot of that is physics and math stuff. So now we're getting to the actual electronics or electrical engineering stuff. So now what I want to talk about, and this is very important, I want to talk about AC oppositions. All right, so here we go. What do you mean AC oppositions? Well, in DC, there's only one kind of opposition that behaves a certain kind of way. That opposition is called resistance, and resistance acts to oppose oppose the flow of current, and in doing that, it produces heat. So you learn that really well in DC. In AC, we have several types of opposition depending on what kind of element we have. We have resistors, we have inductors, we have capacitors, and each of those devices can introduce opposition in a different way. And so the question is, all right, when I have like a resistor, an inductor, a capacitor, how does it affect the voltage waveform or the current waveform? How does it affect those? And that's the question we're trying to answer. So in doing this, we're going to learn about all the AC oppositions. We'll talk about all the AC oppositions. So we're going to start with the very first one, resistance. That's the one you know about. What is resistance? Well, you might remember from DC that resistance, if I take a piece of some kind of conductor, it's composed of atoms. I'm drawing these spheres, but the atom is really a combination of a nucleus and electrons, which are moving around the nucleus at the speed of light. So I feel okay drawing these balls around there, these little spheres, because all those electrons are moving around so fast that they're literally everywhere at once. So there's like a sphere that's charged negatively because those electrons are just going around there everywhere at once. And so what happens is when you apply a voltage across the wire, then the electrons that are free to move, they are drawn this way by a force called electromotive force, which you get when you separate charge to give you a voltage. And then being drawn into the wire, they hit these atoms and they bounce around. And every time they collide with one of those atoms, they give up a little energy in the form of heat. So they bounce around like a billiard ball. So I call this the billiard ball effect back in DC. But eventually, the voltage will pull this or force it through to the other side. But it has to undergo those collisions, and that's what we mean by resistance. So that's the path of one electron. We don't move one electron. We move trillions and trillions of electrons each second. And so all those sum total collisions, that's what you feel when you put your hand around something and it heats up. So that's what I mean by resistance. And so what I want to look at is how does resistance affect the voltage and or current waveform? How does it affect it? If it affects it. And we kind of know what resistance is. So this one I'm kind of going at it that we already know what it is. We get to the other one, we're going to discover a new type of opposition, several new types. So let's look at resistance. And let's go over what we know. We know that to calculate resistance, I got to use Ohm's law. And we know it's pretty simple. We know that resistance equals voltage over current. Now, I'm going to make this more general because what I'm going to say is opposition equals voltage over current. Any kind of opposition in the AC circuit is going to equal the voltage across that opposition divided by the current through that opposition. And the reason I'm writing it this way, because as I said, there's going to be other oppositions that's not resistance, which we'll get to. But right now we're dealing with resistance. Well, so let's say I have a circuit and I want to calculate the resistance. Let me give you the circuit. I got an AC circuit and I got a resistor. So here's my resistor. And I tell you that this right here, that voltage is VP sine omega t. And I tell you that a current flows through the resistor, and that current is IP sine omega t. Now, why? Notice I have the same angular velocity here and here, and the reason is a current produced by a voltage will have the same angular velocity as that voltage. Hopefully, if you understand the way the generator works, since the generator angular velocity is given the voltage's angular velocity, and since the voltage is actually making the current, those angular velocities have to be the same, which means the frequencies are the same. There's only one frequency here. So if I have this voltage waveform, this generator giving me this voltage waveform, producing this current, that's a script I, by the way, producing that current flowing through this resistor, if I want to calculate the value of the resistor, just like in DC, I use Ohm's law. So what would that look like? If I want to calculate it, well, actually, let me show you this. Let's calculate the actual current. So I want to find the current, and I think we did this before. If I want to find the current to get this, how would I get that? Well, what I would do is I would take the voltage waveform, and I would divide by that number R. Okay, so I would divide by R. So I'm able to take this, which is that, V equals, actually, let me just write out this will be VP sine omega t. I'm going to divide that by this value, R. That's how I get this. Now I'm going somewhere with this, so just follow me for a second. If I want to know the current in the circuit, I take the resistance and divide it into the voltage. If they give me the voltage like this, then to do that, all I got to do is just take this, and that'll give me IP. If I take VP over R, that gives me IP. And then the rest of this part stays the same. So it's sine omega t. And that's the important thing I want to show you. That when I look at the waveform, the original voltage waveform I started with, I look at this part of it, and the new waveform I get by dividing the V by R, I get current. I look at this part of it, they're exactly the same. They have exactly the same angular velocity, and they have exactly the same phase angle. In this case, it's 0. If I had a phase angle here, like plus 30 degrees, that phase angle would be transferred over here. When I do this division, it doesn't affect any part of the sign. So what that means is that if they have the same angular velocity and they have the same phase angle, here's what they look like when I draw them on the graph. When I draw them on the graph, let's say I'm going to draw the voltage. Well, it looks like a sine wave. It looks like this. So let's just say that's the voltage. And now I want to draw the current. Remember how I got the current? I got the current by taking that voltage and dividing it by resistance, and that gave me this equation for voltage. But if I want to draw it, I got to draw it like this. What I'm trying to show you here is if this green is the voltage and the blue is the current, they zero at the same place because they're in phase. By doing this math right here, by dividing this time domain for voltage by resistance, I see I end up with a time domain for current with exactly the same angular velocity and phase. So that means that voltage and the current waveform in this circuit are in phase. They look just like that. That's what I want you to remember. Two things. or three things. Number one, resistance comes from that Billiard effect, thing that we talked about last semester, the electrons from the current colliding into the atoms of the material that they're flowing through. When that collision takes place, a little energy is going up in the heat. We said produce heat. And when I get a voltage to cause a current, then that current and voltage is going to be in phase. And as proof of this, you just go through the math I did here, and you see that the argument for this sign, the voltage sign, and the argument for the current sign are exactly the same. So when you graph them out, they have to be in phase. They have to zero at the same point. So you want to remember that if all I have is a resistor in the circuit, the voltage and the current are in phase. That's the takeaway from everything I said. If you don't understand anything else, you got to understand that when I have a purely resistive circuit, the voltage and current are in phase. And what I attempted to do here was to prove it using this math and the logic, if you can follow it. Okay? So for a resistor, V and I are in phase. Any questions so far? I know that's a lot. We talked about derivatives, which we haven't applied yet. We talked about how does resistors affect voltage current waveforms. I'm showing you that they end up in phase if you don't have a resistor in the circuit. So does anybody have any questions over anything we talked about so far? All right, well, I want to move to the next component then. Let's see, on the topic sheet, we just dealt with, if you have the topic sheet, the first thing on the topic sheet was understanding the concept of a derivative. So we went through that. Number two is the response of a resistor to a sinusoidal voltage. That's basically what I just did. Put a resistor up there and wanted to see what the voltage and current relationships would be if I graphed them. And now we learned that if I have only a resistor in the AC circuit, the voltage and current are in phase, which means they zero at the same point and they peak at the same point. So for the next one, it says the response of an inductor to a sinusoidal waveform. So you might remember from DC, an inductor is nothing more than a coil of wire. So instead of my circuit having a resistor in it, it now has an inductor in it. Like that. And here's my voltage waveform. And if you remember, we use a symbol L for inductance. So how does this act? What would this look like? How do the voltage and current waveforms relate? What can I get out of this? Well, what I want to talk about is this new opposition. This is another kind of opposition here. So we got to go back to DC to see how does an inductor introduce opposition into the circuit, any circuit. And the way I'm going to show that is, just go back to DC for a second. This is something that's easy to understand. So I got a switch, and I got an inductor. I got a switch, I got an inductor. And you got to remember Faraday's law. Now Faraday says that if I want to induce a voltage, I got to have three things. I got to have a coil or a conductor. I got that. I got to have a magnetic field. Well, when I close this switch, current will flow. If you remember, current always produces a magnetic field. But the third thing I gotta have is motion or movement. I gotta have movement of the magnetic field and or movement of the coil. And I'm not moving the coil here. Well, here's the trick. Normally, when we show graphs of DC over time, say this is current or voltage over time. I show it like that, and you say, oh, that's a straight line, that's DC. But that's not really correct, because what this is saying, which is incorrect, is that right here at t equals 0, right here, as soon as I close the switch, the current goes up to steady state instantaneously. It goes up from here to the max value in no time, and you know that's not possible. It actually takes time for the current to ramp up. So a more accurate way to draw this when I turn on the switch would be to draw it like this, to indicate that when I close the switch, it takes time for that current to shoot up there. Now, the reason we can get away with drawing it all the way over is because usually, if I look at the time between zero current and the time it reaches steady state, this little delta t right there is so small, it's so tiny, you can ignore it. It's like having $1,000 in one pocket and 2 cents in the other pocket. You don't think about the 2 cents. So normally we can ignore this because it's so tiny compared to all the other times. But we can't ignore it right here, because during the time that it takes to go from 0 to steady state, the magnetic field is doing this. It's increasing. And when the switch is closed, if I open it back up, the magnetic field is not sustained by the current anymore because the current's not flowing. So that magnetic field is going to collapse, and I have Faraday again while that field is collapsing. So while the field is building up or collapsing, it actually develops a voltage from Faraday's law across it. I'll just call it VL, but it's called a counter EMF, or counter voltage. In other words, if the battery during this buildup, if the battery is pushing the current this way, while that magnetic field is moving, it's trying to move a current back the other way. So these currents are actually flowing in the circuit opposing each other. In DC, I said they were bucking each other. I don't know if you remember that term or not. So this is not the billiard ball effect. This is different. This is not resistance. Resistance is the current electrons colliding with the atoms that make up the material through which the current is flowing. This is a more of a current voltages opposing each other, or currents opposing each other. I say that they're bucking each other. So this is not resistance, but it is a type of opposition. If you think of currents doing this, you can kind of imagine that opposition in your mind's eye. So that's kind of where the opposition, I just want you to be clear that the opposition from an inductor is not the billiard ball effect. It's not the same as resistance. Now, having said that, let's look at something. Now, I don't know if you remember this, because this is where we only spent a little bit of time with this in DC, but I gave you Faraday's law. Here's what I gave you for Faraday's law. V equals N d phi dt. Now, I don't know if you remember that, but N was the number of turns on the coil. Remember, that's the magnetic flux. And now you know this d phi dt thing is a derivative. This is the change in flux over change in time, and that represents movement. And so that was the way we talked about it in DC. But I'm going to give you another form of Faraday's law. It looks like this. And you can actually, they're kind of related, because if you think about it, we have DI here, here we have d phi. This is current, that's flux, but flux is really created by current. So the fact I can write it this way should not be surprising at all, because the cause of this is that current. So the magnetic field is going to change like the current changes. So it doesn't matter if I look at how the magnetic field changes or how the current changes, it's still going to represent change in the final analysis. And then even these two are related, because this N is how many turns are on the coil, but the coil itself is the inductor. So this is just saying instead of using the number of turns, let's use the inductance. So to get Faraday's law to work to find this induced voltage, I can use the number of turns on the coil or inductor times how fast the flux is changing, or I can use the actual inductance times how fast the current is changing. This is just two different ways to write Faraday's law. And I want to use this way. If I use that way, what I want to do is, using this, I want to graph the voltage. If I put in a sine wave into this inductor, let's graph the voltage and let's graph the current. What would they look like? Let's graph that. I want to graph it. All right, so let me move this off to the side. What I want to graph is V induced equals L di dt. So let's look at exactly what we're graphing. I'm going to call this VL, because that's the inductor, and VL will be the voltage across the inductor. So this is VL. And the current flowing into here from VL, we'll call that IL. All right, so it looks like VL is equal to, not I, it's equal to, remember this derivative is how fast I is changing. And how fast I is changing, this di dt, what that is the slope of a tangent line. This is the derivative, and this is the slope of a tangent line. So if I want to find the voltage, what I got to do is get the current graph, which is a sine wave, and then see how the current is changing, because that's what this part of it represents, how fast the current is changing. So let me make a graph of current over time. So this is current, and that current is going to look like a sine, you know. If this is the circuit, and that's the sine, that's the generator, then this current produced at I is going to be a sine wave. So now let's look at what V looks like. So V is equal to not I, but is equal to how fast I is changing. If I write it using the proportionality sign, I can do this. V is proportional to not I, but di dt. What is di dt? Di dt is the slope of a tangent line. And so, where's my tangent line? If I want to, I don't know what I did with my pen, my tangent line, but if I want, here we go. If I want to see what this looks like, I gotta get the slope of this current. So this is current right here. That's the current waveform. And I can see like right here, at t equals 0, that tangent line is the highest. It has a really big slope, which means that that number right there, which is the slope of this, is really, really big. So V is going to be huge. So V might look like this. It's going to start off really high. Now this point right here, 90 degrees, let's see what happens when I move my tangent line from 90 degrees, from 0 degrees up to 90. Look at what happens to my tangent line. If I start here, my slope, this value in the circle, this represents di dt, is large. As I move it towards 90 degrees, it's getting smaller and smaller and smaller. Matter of fact, at 90 degrees, my slope is 0. So this is starting from a large value. As I move towards 90 degrees, it's going down to 0, which means V is going to follow it. So V is going to start up really high, and as we move towards 90 degrees, it's going to go down to 0. And then if I keep going at 90 degrees, if I keep going with my tangent line, now look at what's happened. Tangent line is getting steeper and steeper, so the slope's going up. But this was a positive slope. This way the slope is negative, which means it's getting bigger in the negative direction. So I can see that it's going to go down here. It's going to get bigger in the negative direction. And once you give me this part of it, I can just kind of use symmetry and just finish drawing it. Here's what it's going to look like. If I have the inductor, and the inductor behaves like this equation says, the voltage is L di dt, then since this voltage is related to a derivative, this is how the voltage waveform is going to look. And you can see that they're not in phase. Matter of fact, if you look at it close enough, look at this. This angle right here is 90 degrees. So what is that saying? If you start right here at, this is T, and this is T. At T equals 0, a couple things I want you to get out of this. At T equals 0, the current hasn't even happened yet, but look at the voltage. For this inductor, the voltage is at, that's a V by the way, the voltage is at maximum. So in time, the voltage is happening before the current. You can see here in time T equals 0, the voltage is max. Here, T equals 0, the current is 0. So one thing to notice is, for an inductor, the voltage happens before the current. And then, not only that, that voltage is at 90 degrees. The phase is 90 degrees. If I pull it back this way, the phase is 90, where the current has a phase of 0. So now I want to go back to that equation that I talked about earlier. We know that resistance equals voltage over current. But I want to rewrite this. I just want to say opposition. Any old opposition is equal to voltage over current. Why am I doing that? Well, because this is not a resistor, but yet it has opposition. And if I want to find it, I don't know what to call it, so I'm just going to call it X. So this opposition X. In math, when you don't know what something is, you call it X. So let's just call this opposition X. Whatever this opposition X is, I know to get the value of it in ohms, I got to take the voltage and divide by the current. And that gives me the opposition, whatever it is. Well, my current is at 0 degrees. If I look right here at T0 and T0, my current is at 0 degrees, so I can write it like this. This is I at an angle of 0 degrees. And while my current is at 0 degrees, look at my voltage. My voltage is at 90 degrees. So when I divide this into volts, my volts is at an angle of 90 degrees. So that's really strange. I got this opposition, X, from a thing called an inductor. And look how weird it is. Number one, I can see that when I have this opposition with this inductor, the voltage happens before the current. There's a phase difference or phase angle between the voltage and the current, and that phase angle is 90 degrees. So when I divide V by I, V is at an angle of 90, while I is at an angle of 0. What that means is this thing right here, that opposition, is going to have an angle of 0, 90 minus 0, 90 degrees. So if you follow the math and the argument, here I have an opposition that's not resistance, and it has an angle that's not 0. You remember, for the resistor, the current and voltage were in phase. So when I divide, if I divide for a resistor we drew the graph like this. We have voltage and we have current. They were in phase. So if I wanted to figure out the resistance, I take the voltage divided by the current. But since they're in phase, this phase angle is 0 and this phase angle is 0. So the resistance, which is what I get when I divide V by I, if this is 0 and this is 0, 0 minus 0 means that this is at an angle of 0. So resistance doesn't have a phase. That Butterbaugh effect doesn't have a phase, but the opposition caused by this inductor does have a phase, because you can see voltage is at 90 degrees when current is at 0. So when I do the math to get V over I, which is opposition X, that opposition X has an angle associated with it of 90 degrees. Well, that's a problem, because that means that's not a real number. Real numbers are on the real number axis, and they can only have a phase of 0 degrees or 180. This is something else. It has a phase of 90. The phase 90 means what? It means it's a imaginary number. So here I have in nature a kind of opposition that an inductor will give me that has a phase associated with of 90 degrees, which means it's not a real number. It's an imaginary number. So I can't use a regular axis to represent it. I got to use a complex number to represent it. And so let me just name this X. This opposition from an inductor is called reactance. And usually what they do is they'll put a little L here for inductor. This is the inductive reactance. And I'll show you something in just a minute. But the thing to know here is that inductive reactance has an angle associated with it. So if I want to graph it, here's what my graph is going to look like. I got the two axes. Now this was our real axis, and this was our imaginary axis. Well, I just showed you, since resistors, when I have a resistor, only a resistor in the current in the circuit, and I divide voltage by current, then the resistance has since the voltage is at an angle 0 and the current is at an angle 0, the resistance angle is 0 too. In other words, resistance is a real number. So this axis right here, I'm going to get rid of this name right here. And I'm going to call this the resistance axis. And I want you to do the same thing. This is resistance. Resistance is always a real number. And I just showed you that this new kind of opposition, I'm calling reactance, and I'll tell you why in just a second, is an imaginary number. So I'm going to call this the reactance axis. It's imaginary because the angle associated with it, the phase, is 90 degrees. So if that's the case, then XL basically is this part of the axis, the imaginary axis. So anything from here up is inductive reactance, and anything from here over on that axis is resistance. But if I go back this way on my resistance axis, the resistances get smaller and smaller and smaller, and this represents zero resistance. I cannot keep going because there's no such thing as a negative resistance. So since I can't have a negative resistor, like a negative 10 ohms, I don't really need this part of the axis. I can get rid of it. So that's what I'm going to do. I'm going to get rid of this. So I got a resistance axis, I got a reactance axis, and I just showed you part of this reactance axis is reactance that comes from an inductor, and they call that inductive reactance. Let me write it down. Inductive reactance. And I tried to show you where that angle of 90 degrees came from, going through that map I went through with the graphs. And you may have to go back and review the video to actually listen to it a couple times. So that's what happens if I take V at an angle of 90, I at an angle of 0. I get an opposition that we're calling it reactance, in this case inductive reactance. It has a phase of 90, so I can't put it down here. I got to put those ohms right here. Okay, all right, well, that's a lot, I know. But what if we change out the inductor and we put in the capacitor? What would that look like? The capacitor, what would that look like? How does that behave in an AC circuit if I put in the element C? And I kind of want to go through the same argument again, but I'll do it a little bit quicker. So now I have to have we call it the differential equation that says how the capacitor acts. And what that looks like is this. The current to a capacitor is equal to C dV dt. The current to a capacitor is equal to the value of the capacitor times what? This thing right here, dV dt, which means, again, that's a derivative. That's the slope of a tangent line. So if I want to see how this looks on the graph, the sign, I got to take into account that that's a derivative. You got to make a graph based on the derivative. So let me clean this up, and we'll go through this last argument here. Hopefully you understand. So when I kind of go through the same thing I went through with the inductor, so hopefully you can follow the logic if you didn't get through it the first time. So what I want to do is I want to draw the current waveform for this. What does it look like, knowing that it's related to C times the V dt? And so to get the current, I got to look at the voltage. So I'm going to make a graph, my first graph. This right here represents the voltage. So that represents V. That's that. All right, so how does that, if the voltage looks like this, how does the current look? All right, let's make another graph. For current. And again, I'm going to put this point in here at 90 degrees. Now, the current is proportional to not to V, but to the dV dt. So the current is proportional to dV dt. The current is proportional to how fast the voltage is changing with time. And this thing right here, dV dt, is a derivative, which means I got to use my tangent line to see when this part right here is big, when it's small, when it's positive, when it's negative, when it's zero. So let's test it out. So if this is if this sine wave is V, the slope of this tangent line represents dV dt. So right here at the beginning, I can see that it's the highest. dV dt is really high. And as I move towards 90 degrees, dV dt goes to zero. That slope goes to zero. That means the current down here, since I'm multiplying it by that really high number, that current is going to start off at a really high value. And then as I move my tangent line to 90 degrees, I can see that this part, dV dt, is going to zero, which means my current is going to go to zero. So I can just kind of see how that's going to go. I'm going to start out here. It's going to go down to zero. If I keep going past 90 degrees, now my slope is getting larger again, but in the negative direction. So I got to go larger, but in the negative direction. So that means it keeps going down like this. And once I get that part of the graph, I can just kind of see how that's going to go. It's going to go like that. So now when you look at it, it's the reverse of what I had when I had the inductor. With that capacitor in there, it looks like, if you look at this close enough, that because of that differential equation, the relationship between I and dV/dt, it looks like here, notice the voltage at t equals 0, the voltage is 0, but the current is already at its peak. The voltage hasn't happened yet, and the current is already at max. And this phase angle right here is 90 degrees. It's like it pulled it back over 90 degrees. So I'm going to find the opposition that this thing produces, which is not the billiard ball effect, it's not resistance. That opposition is going to look like this. We said opposition is going to equal the voltage over the current. Well, I don't know what to call it again, so I'm going to call it X, because it's not resistance, it's something else. So I'll call it X. And then opposition X is going to equal the voltage, but look at the voltage here. The voltage is at 0 degrees, so I got my voltage at an angle of 0 degrees, and my current has a phase of 90. So my current is at a phase of 90 degrees. So now what I do is when I divide this, I divide V over I, I get this opposition, but look at, it has a phase associated with it. If I divide these two numbers in polar form, 0 minus 90 is a negative 90. So now I have an opposition that has a phase angle of minus 90. So again, I can't plot that on the resistance axis because it's at minus 90 or 270. So let me go back to that diagram I had before and start over. Now we're dealing with real numbers for resistors and complex imaginary numbers for reactance, whether the reactance is from a capacitor or an inductor. So our diagram for our complex numbers used to look like this. This was the real number axis, and this was the imaginary number axis. Well, I'm going to change this to resistance. Because resistance always has a phase of 0. And I know that I will never measure any negative values of resistors, so I don't need this part of the axis. And then I showed you that this value X, this reactance. Reactance is going to have a phase of minus 90 if it's from a capacitor, or plus 90 if it's from an inductor. So we got to use imaginary numbers for that. So I'm going to change that from the imaginary axis to the reactance axis. And what I showed you before was that the reactance from an inductor, XL, is here because its phase is 90. And I just showed you here that the reactance from a capacitor, we'll call that XC, has an angle minus 90. So these oppositions, let me write them down. And I want you to study the names. What I have is resistance. Resistance has a phase angle of 0 degrees. I have inductive reactance. That's XL. It has a phase of 90 degrees. And I have capacitive reactance. XC, and it has a phase of minus 90 degrees. So you want to remember this. Those are the oppositions we talked about so far. Now, to get resistance, you know how to do that from DC. Resistance is just usually you'll know voltage and you'll know current, and that'll give you resistance. And you can get reactance and capacitive reactance and inductive reactance the same way, but they actually have formulas. So let me give you those formulas. I'll give you one for XL and one for XC. So this is 2 pi FC. I'm sorry, F. And the units are in ohms. So if I want to calculate the magnitude of the inductive reactance is 2 pi FL, where F is the frequency of the generator and L is the value in henries of the inductor. And for capacitive reactance, it's 1 over 2 pi FC, again, where F is the frequency of the generator and C is the value of the capacitor, and its units are in ohms. And one more thing. Remember when I drew the sine wave, I drew one like this, and then the other one was out of phase by 90 degrees, and we said, well, that value happened first, or that value happened second. Well, easy way to remember that is this. If you write this out, Eli, the Iceman. This is just a way to help you remember which happens first. Eli, the Iceman, so write that down. And the way this works, this L, we use that means we have an inductor. And the C means we have a capacitor. And so E is for voltage and I is for current. So the way you would say it is, if I have an inductor, just a purely inductive circuit, nothing but an inductor in an AC circuit, the voltage happens before the current, or the voltage is going to lead the current by 90 degrees. The phase between them is 90 degrees. That's only true if I have only a inductor in the circuit. If I add a resistor in the circuit, that's going to change that phase angle. But for just an inductor, L, E happens before I, or the voltage leads the current by 90 degrees. Here, C is for a capacitor. In this circuit, I happens before E. So we say for a strictly capacitive circuit, the current happens before the voltage, or the current leads the voltage by 90 degrees. I can say the current leads the voltage, or the voltage lags the current, either way. So this Eli the Iceman is something you want to remember. Wow. So I've talked a lot, almost the whole 2 hours. I guess you guys are still with me. I think what I want to do is, I've done everything on the sheet. If you go back and you look at response of the basic RLC elements, I think what you guys should do is just kind of read over this. And I've actually done the practice problems for you at the very bottom of this. I've done the practice problems, which is just basically drawing graphs from the differential equations to help us understand where these angles come from. But this diagram right here is important. It's called an impedance diagram. Let me write the name. We'll use this a lot. It's called an impedance diagram. And next time we get together, I think I'm kind of out of gas now. I have another sheet up on Blackboard where we practice calculating XL and XC. So next time we get together, I'll review this. I want to show you one more thing before we sign off. If I have a value right here, say I have a value right here. Let's just say 10. That would be 10 ohms. That means I have a resistor that's 10 ohms. If I have a value right here, let's say that that's 8, but it'll be a J8. That will mean I have an inductor with a value of J8 ohms. Or maybe if I have a value down here of minus J5, that would mean I have a capacitor whose value is minus J5 ohms. Now notice, even though capacitance is in farads and inductance is in henries, using these equations, you convert the henries or the inductance or the capacitance to ohms. That's what these do. It converts it to ohms. Any opposition is measured in ohms. But depending on which axis I'm on, this represents an inductor that's 8 ohms, that's J8. Or right here, this would represent a capacitor, XC, that's 5 ohms, or minus J5 ohms. Well, what happens if I take that resistor and this inductor, and I connect them together like that? Then what I would have is I would have 10 plus J8 ohms. And I'm no longer on the axis. If I go over 10 and up 8, that means my point of opposition is right there. So it's not resistance purely, and it's not reactance purely. What is it? Well, if you take resistance and you add to it reactance, you get another opposition called impedance. And that's what I want to talk about next class. That's why this is called the impedance diagram. So guys, I know I did a lot. I hate to do a lot of talking because you just listen to words, and then without practicing the math of it, it's not really driven home until you do calculations. But because of the nature of the material, I had to talk for 2 hours. So here's what we'll do. On Wednesday, we get back together. There's this other sheet that you want to make sure you print off Blackboard. And then actually it says reactance practice calculations. I want you to have that printed out, and we'll go through and we'll work this, and we'll be using these equations, and it'll help us to understand reactance and impedance. And then what we'll do is we'll take that knowledge and then we'll apply it to a circuit. How will we solve a series circuit or a parallel circuit with this stuff? And that's kind of where we're heading. So review the video. I did put a homework for you up on Blackboard as well as another lab. I think the reading that I assigned, I forget the section, 14.5 or something, deals with phasors. But if you want to read ahead on reactance, if you're reading the book, that might help clarify some of what I talked about. You can read about capacitive reactance and inductive reactance. That might help you. But we'll get back together next class and we'll do some more of this, and I think it'll be a little more clear when I do some practice problems. Okay, so we went through a lot. Does anyone have any questions over anything we talked about, or maybe something we didn't talk about? Any questions at all before we start off?
I had a question. So you said you upload the videos of the classes. Where do you upload them?
Okay. Oh, no. You know what I did, Jacob? I tried to upload it the first day, but these videos are so long. What I did last semester is I put them up on YouTube, and I created a playlist for each class that I taught. But the classes were only an hour long. With these classes being 2 hours or 2.5 hours, it took so long for them to upload to YouTube, so I didn't even upload them. But you have access to all the videos on Blackboard. If you go to your Blackboard, it should be a link that says collaborate. And when you click on that link, this is where you go to sign onto the course, onto the video stream. There's a little tab that if you click on it, it'll say past recordings. You go back and see all the recordings that I made. So all the recordings are on Blackboard. So if you need to go back and watch a previous video, it's on Blackboard. And if you can't find it, send me a text, and I'll call you on my landline, and you'll have your computer, and I'll have mine, and I'll help you find it. But it is on, the videos are on Blackboard, and they're stored there under the Collaborate link.
Okay. Yeah,
Any other
I see it
questions?
now.
Okay, well, guys, I know that was a lot. Does somebody have a question?
Yeah, it looks like we don't have the, I don't see anywhere where you actually updated in the course documents where you actually put these two sheets for AP opposition.
Really?
Yeah, it's not on there. For June 8th, it just says phasors and complex numbers, but it doesn't say anything about what you're
AC opposition?
Yeah, I don't see any forms at least. I mean, I've been looking for them.
Okay. Okay. Well, thank you. I'll go up and I'll maybe I missed that one, but I printed it off, so I thought I uploaded it. But I'll go up and I'll put it up there, and you'll have it. You can print that out for next class. So thank you for telling me. I'll take care of that.
No problem.
Right away. Guys, thank you. That was a long lecture. I know it was a lot of just listening to talk, but it'll make sense next time. So thank you so much for being so patient. Have a great rest of the day. Enjoy the week while it's cool, because at the end of the week, we're going to hit 90 again. It's going to be humid. So I'm going to hate that. So I will see you guys on Wednesday. Anything come up, just send me a text.